takes less than an hour, so I'll use a part of the time for propaganda. So this talk is being videotaped, and I should explain why. Oh, sorry, it's being videotaped, but it's not being spoken. Is it okay? Okay, so and I should explain why. So basically, well, Nathan Danfield showed us or was going to show us a YouTube video of the tutorial for his program, and I guess the point is that the medium now exists and the delivery is available, so why not use it? Okay, and besides, this particular subject is a subject that hasn't been visited for maybe 40 years or so, or not much has been written about it in many years, and so all record of it is in rather sort of black and white style journal articles. So it, if I'm making a color presentation of it, I may as well make it available. However, I'm not using YouTube, and this is where the propaganda comes. But instead, I'm using my own software to display this, to put the video on the web, on the internet. So here is an example of a video being shown with my own software. This is, I'm sorry, again myself giving a talk in the class that I'm giving. And in fact, the content of the talk is a presentation of this video. So you can see it's more or less the same. But the point of not using YouTube is that I actually do better.
I can't quite make out what's in the upper corner.
Well, do you want me to make it sort of larger?
Yeah.
I mean, it's doable, but okay, no, I mean, if you look at it on your own screen, you'll do better. Okay? But the point of using my own software is that it's actually better. So I allow you to comment on any specific time. So if you click here, oops, nothing happened, but sort of if you click here on your screen, it will open another window where you can add a comment. It will be a comment associated with second 59 of the talk. And then it will appear here, and here are the comments that are already here. Now, these comments were added with a wiki-style interface, so anybody could add, and then when you go through the talk, it highlights the comment that's right next to you, that's closest to you, and if you want to jump to some specific place, I don't know, the definition of M singular naught, I mean, not that you would care, but here you go, I just jumped there. Okay, so I actually do better than YouTube, and hence I do it. The other the other point I wanted to make before really starting is to explain that actually this is not what I normally do, and the only reason I'm doing it right now, it's not the subject of my research, I'm not an expert, I don't know anything about this subject beyond the color pictures that I'm about to show to you. And the only reason I'm doing it is that I've been having a miserable semester. I taught too much and did too much administration, and I had to give myself a candy. So this is the candy that I'm giving myself. And just to emphasize how pathetic I am, I'm eating this candy twice. Okay, so I gave it first time as a graduate student lecture with fewer color pictures, and then I added some more color pictures, and I'm giving it now again. Okay, and eating it again. Anyway, the talk follows the handout. You're holding the handout. Everything that will happen on the screen is also in front of you. Okay, and now let's go on to the content. So, Hilbert asked if a certain specific three-variable function, so he wrote specifically a function, something like the roots of a polynomial of degree 7 as a function of the coefficients. And of course, we know that we cannot solve polynomials of degree 7 by radicals, but he asked, well, maybe you can write this, the value of the root as a function of the parameters using less than functions of three variables. So maybe you can write it as some composition, strange, bizarre composition of functions of two variables or less, okay? And then in 1957, Kolmogorov and Arnol'd showed something much stronger. So every function, every continuous function, maybe I should say every function today will be continuous. So when I say a function, I really mean a continuous function. Okay? So what Kolmogorov and Arnol'd have shown is that every function of any number of variables can be presented as a finite composition of functions of a single variable, and only one single two-variable function is required, and this is the function plus, or could be taken as the function plus. Okay? So in some sense, the only real two-variable function is the function plus. Everything else is just it souped up with one-variable functions. Okay? So for example, is there some pointer here?
There's a couple laser pointers.
Yeah, no, other than the one that I'm holding. Laser pointers are silly. I mean, it's hard to see them. Okay, but anyway. So, for example, the function x times y is one variable function, exponential, of log of x plus log of y. So I did use log, but otherwise it's one variable. Sorry, I did use plus, but otherwise it's one variable. Okay? Likewise, x to the power y divided by z can be written as, I hope the formula is right, but the point is clear. The only two-variable function being used here is plus, and everything else is one variable. Okay? Now, what about if it was the Riemann zeta function? Okay? So here is the Riemann zeta function shown three-dimensionally. Sorry, it's really the 1/3 to make the colors nice of the real part of the Riemann zeta function of x plus iy on some very specific rectangle on the complex plane, which happens to contain two zeros of the Riemann zeta function, but otherwise it was chosen completely arbitrarily for aesthetic reasons. Okay? And then you can ask yourself, okay, sorry, here it is shown as a three-dimensional thing. Here it is shown with sort of where colors represent values. So basically, it's like a barometric, not barometric, a weather map. Okay? So like the blue stuff at the top is very high values because you're high up and it's cold. And the red stuff at the bottom is where you're below zero. In fact, purplish stuff at the bottom is where you're below zero. So it's really, really hot. I mean, below zero in altitude. So it's really, really hot. Okay? Anyway, the question is, can you take a function like that and present it as plus and single variable functions? And here's the theorem. Okay? Let's fix an irrational number lambda, and it really doesn't matter what it is, but it's best to take the most irrational number there is, which is square root of 5 minus 1 divided by 2. Okay, it's in some sense the number which is farthest from the rationals that you can get. Okay? It really doesn't matter what you choose. Anyway, let's fix it from this point on. Okay? And then the statement is, there exist 5 continuous functions, phi I, phi 1, phi 2, phi 3, phi 4, phi 5, going from 0, 1 to 0, 1, so that for every function f is the function we want to present. So f is like the Riemann zeta function. So for every function f defined on the unit square, your exercise at the end will be to generalize it to higher dimensions. For now, I'll just do 2 variables. So for every function f, you can find a function g, of course continuous, so that f of x and y is the sum as I goes from 1 to 5, so it's a finite sum, so it's a finite composition of the 2 variable plus, of g evaluated on phi I of x plus lambda phi I of y, and again this is a composition, this is a plus and compositions of one variable functions. Okay, so that's the statement. Okay so far? Okay, good. So the proof will have 4 steps, And the 4 steps are not lemmas, okay? It's not that like the first step is a prerequisite for the second step. It's more like I will make it more and more sophisticated and achieve more and more as I go through the steps, okay? But anyway, here is the first step. I'm only asserting that I can approximate the function f up to an epsilon on 98% of the unit square. Okay? So, in other words, for every epsilon greater than 0 and any function f, I can find a function phi, a single function, this time I don't need 5, a single function phi, and a single function g, so that f minus g of phi plus lambda phi of x plus lambda phi of y, is less than epsilon. So in other words, this composition, which is of the type that we like, approximates f to within epsilon on at least 98% of the area of the unit square. Okay? So this is just the first step. Okay. The key to the proof is to purify chocolate bars. So here is a chocolate bar, right? You can see, and and I have to explain what to purify it means. So you know, chocolate bars are made out of chocolate squares and gaps in between, sort of used to break the chocolate, right? If you're the kind of people who shares. And to purify a chocolate bar would mean to make the squares small and the gaps big. So in other words, to make the chocolate bar purer, okay? And here is a schematic view of a chocolate bar. So a chocolate bar has, well, the overall rectangle is the bar, and it's divided into 9 squares in this particular case. And each square is brown, okay, but it has a filling. So like this one is filled with mint, and this one with punch or something, and this one with chocolate mousse. So the fillings have different colors. And let me now purify it. So how do I purify it? I apply to both the x-coordinate and the y-coordinate a function phi that looks like a step function like this. Okay? So it has sharp rises and then relatively flat parts. And the sharp rises are timed to be on the gaps. And the flat rises and the flat areas correspond to the projections of the cubes, okay? So if you take this rich chocolate bar and apply to it phi times phi, you get a poor chocolate bar as shown here, okay? So the image of a point here via phi times phi will be a point inside the square right here, and the square grew much smaller because I applied to it a function which is rising very, very slowly, okay? In a second, we will see why this is useful, but let me introduce a tiny bit of terminology just so that I can refer to the pieces of the pictures that I will draw later, okay? So here is a piece of this step function magnified, and I will refer to the sharp rises as rises. I will refer to this part here as the flat. The flat has a delta x and a delta y, and delta y over delta x is what I will call the slope, and it's generally a small number, okay? And the size of the square is 1 over n. It's 1 over the number of squares that I have. And finally, if you look at delta x, so this size from here to here, and divide it by the overall size of a single square, so delta x divided by size is what I will call the fill factor. So it's the part of the chocolate that's actually filled. Okay? Anyway, let's go back to the picture and continue the description of the proof of step 1. Okay? So the next thing that I do is I apply a projection from the square to the real line. And the projection is the projection that maps psi eta to psi plus lambda eta. Now, lambda was an irrational number, and all my choices were rational, so the centers of these squares are in rational coordinates. So when I project them in an irrational direction, they project to distinct points. Okay? So in other words, all of these projection points are different from each other. Okay? Furthermore, they're positive distance away from each other. So if I had chosen my purification function phi well enough, in other words, if I chose the slopes small enough, then the squares will project to little intervals that are disjoint from each other. Okay? So this is sort of the picture, and now let's see how it relates to the problem I started from. Okay? So I want to approximate the Riemann zeta function on the unit square. The Riemann zeta function is uniformly continuous, is continuous and therefore uniformly continuous on that square. So I can divide the square to sufficiently many pieces so that on each piece it would be nearly constant, constant up to an epsilon. Let's pretend that the number of pieces is 3, so it's like this. In the end result, I want the pieces to be colored as the colors of the Riemann zeta function. And if you compare this with the plot of the Riemann zeta function that's still on your handout, you'll find that these colors precisely match the corresponding. So each square here is colored by the color of the Riemann zeta function on the center of that square. Okay? And then, well, this is the approximation I want to get. The way I will get it will be by coloring these squares with the same colors, and therefore by coloring these intervals with the same colors, or in other words, I will choose a function g on the real line whose values on the small intervals are determined by the values of the corresponding chocolate cubes which themselves took their values from the Riemann zeta function. And then I will use this composition going to here and then to here to pull back g to the plane, to the unit square. What is shown on this picture is precisely this pullback. Namely, it's precisely g of phi of x plus lambda phi of y. And as you can see, it approximates the Riemann zeta function to within epsilon. Again, if n was large enough, it would be to within epsilon, on everywhere except the gaps between the original chocolate cubes, meaning, and these gaps could have been made as small as you wanted by choosing the fill factor to be as high as you wanted. Okay? So this is the key point. This is the one picture that you really need to understand. Everything after that is just variations. Okay, but this is the key point. So are you with me? Is this okay? Yes? Even Rich?
I'm with you.
Good, thanks Rich. Okay, so now a few color pictures, okay? So first of all, here is phi of x. Here is a plot of z equals phi of x plus lambda phi of y, and it's colored by the value of z. Okay, so as you grow, as you go up, the color changes. Okay, and what you see is, well, if you set y equals 0, you see just phi of x, and this is the exact same function that was shown before. I suppose before I did it with 3 steps, and here it's done with 5, okay? But it's the same principle. If you set x equals to 0, it means that you look on this side, again, you see the same function, phi of y, except multiplied by lambda. So it doesn't reach as high, right? This point over here is a bit higher than this point over there. Now when I add these two functions, the result look like sort of a cascade of steps or a two-dimensional, what do you call it, steps. There is a name to steps. I don't know. Okay. A two-dimensional set of steps. And lambda is irrational, and therefore, yes?
Sorry, you say Z colored, what is Z?
Oh, Z is just the Z, X, Y, Z of R3. So it's every step is colored, every point in the graph is colored by the value of Z. Z is just its height. Okay? So indeed the colors look like sort of, you know, corresponding to the height.
So things of the same color are roughly the same height. That's
Yeah, so basically if this is blue, it means that, right, exactly. But again, the point here is that I tilted the steps a bit by multiplying the y direction by lambda, and as a result, the flats of no two steps are at the same height. Okay? And this means that if I project those to the z-axis, each step appears like a different interval, so I can set the values of the function g to be what I want on these intervals. So here is the function g that you get, and you see these are the flats, the images of the flats of the steps. And in between I've interpolated however I wanted. Since I have no imagination, I've interpolated linearly. But it really doesn't matter how you interpolate in between the flats. Okay? And you get a very sharp-looking function, but it's a function. And here are those same steps colored by the value of g. Okay? So again, the exact same steps, each one colored, or each point colored not by the height, but instead by g of the height. So each step is colored as it should be colored, so that if we look from above, we will see an approximation to the Riemann zeta function. And indeed, we see an approximation to the Riemann zeta function. If you compare it to the picture of the Riemann zeta function on the upper right side of your handout, it will be, you'll see that it's a reasonable approximation. But again, I don't want approximation, I want equality. So let me explain why this fails to be an equality. It fails to be an equality, for example, because if you consider this square, this green square over here, okay? This green square came from here, which came from here. The inverse image of this green square, of this green interval now, is some interval that goes around this line. Okay, it's some little ribbon that runs around this line. And if you pull the inverse image further, it looks like a path like this. Okay? So at the end result, you have a path of green going from the very top of the picture to the very bottom of the picture. So you'll have a little path of green where it's completely misplaced. Okay, where it's completely wrong. And indeed, if you look at this picture, you'll find that, well, I don't know where the green went, but you'll find that, say, this blue here has a, well, every other point that was geologically formed at the same time as this point, as the points on this flat, is also colored with the same color. Okay? So if you look at it again from above, oops, sorry, if you look at it, well, let's just imagine that we look at it again from above, we'll see errors. Okay? And here is what it is from a three-dimensional perspective. So at the flats, the values are right. Okay, here is a flat where the value is right. Here is another flat where the value is right. Here is another one where the value is right. But unfortunately, in between the flats, in the gaps between the flats, I have huge hills and trenches whose magnitude, whose L infinity norm, is comparable to the magnitude of the function we started from. So in L infinity norm, our approximation is lousy. Okay? So going out of this flat, I have a huge ridge that avoids all the other flats, but makes the L infinity norm horrible. And in between these two flats, there is likewise a trench that came from one of the flats in between, which are hidden, so you can't see them. Okay? So are you with me still? So let's move on to the next step. So now, basically, I claim that I can change the order of quantifiers. Okay? So I claim that there exists a single phi, a single function phi, that works for every epsilon and every f. So in other words, for every epsilon and every f, you can find a g so that this difference will be smaller than epsilon on most of the unit square. Okay? And this is the easiest step, but it's the best pictures I have, so I will spend some time on it anyway. Okay? So the idea is iterated purification. Okay? So you purify, and then you purify what you've purified, and so on. Or said differently, here is a chocolate bar, a 2x2 chocolate bar. Look at the dark brown here. That sets a 2x2 chocolate bar. And now further subdivide it by putting sort of a chocolate bar with even smaller chocolate pieces on top. So these are the 12, this is the 12x12 array of even smaller chocolate cubes. Okay? And then imagine that you continue indefinitely. Okay? So imagine that you then refine it to a further chocolate bar with 120 by 120 pieces. And furthermore, you may as well increase the fill factors as you go. Okay? As you go level by level. And then you find a function phi that purifies, a single function phi that purifies all levels at the same time. Okay? So here are the first three steps of the construction of phi. Phi 0, phi 1, phi 2. The phi I want is the limit of these phis as 2 goes to infinity. So phi 1 is just the red thing. Here it's the identity. Phi 2 looks like the phi we had before. It's in green. And again, it has sharp rises and flats in between. And then phi 3 improves on that. Okay, but it's clear that you can always improve. So long as the slopes were never 0, you can still subdivide them and make them closer to 0 and with even sharper rises. Okay? So, and it's clear that you can continue. Here is, like before, phi of x plus lambda phi y colored by altitude. Okay? So, you can see the big steps. Right here is a big step. Okay? The sharp rise from this big step to this big step has been subdivided into two smaller steps. And if you look very carefully, you can see that even the big steps are subdivided into sharp rises and flats. Okay, so it's actually kind of hard to see because the resolution is not quite good enough. But if you look on the side, you can see that it's a bit rugged, and also you can see that there is a little bit of shading. Okay, a little bit of well, anyway, that's the picture. Now, suppose I want a rough approximation for the Riemann zeta function. Then I just ignore all the high-level subdivisions. Look at the low-level subdivision. It has only 4 flats, so the corresponding function g will have only 4 intervals that have set values. And then when I color the steps, the cascade of steps, by g, So this is what I get. Okay? And then I look at the answer from above, I get a lousy approximation for the Riemann zeta function. Okay? As good as you could get with a 2 by 2 array. Okay? But then let's do it again, but now look into the second level. So now I have 144 steps, each one at a different height. So so their image on the z-axis are different, so I can set the values of g at these 144 different intervals to be whatever I want. Here's the g that you get. And it looks like a complete mess, but it's still a continuous function. Here is the cascade colored by g. And here is what it looks like from above. Okay? So from above, you can see that it's a pretty good approximation of the Riemann zeta function. However, like sometimes in between two blue pieces, you have something green that came from here, and sometimes in between two red pieces, you have something green that came from here. Okay? Or in this geological formation picture, you can see that all the flats had the right mineral deposits on them, but on the exposed sort of rises, you can see the whole geology of the function, right? Like, so for example, this blue layer here must have come from somewhere, God knows where, from here. It's out of the screen. Oh, from here. Okay? And in fact, it's kind of fun to look at this picture and see see the origin, understand the origin of each geological layer that appears in it. So this is the nicest picture that I have. So this was the purpose of this talk. So we may as well stop here. But since I promised a proof, I'll do the next step as well. Okay? So the next step, now I see the number 5. Okay? So I claim that there are 5 functions, phi I goes from 1 to 5, so that for every epsilon and every f, there exists a g, so that, okay, the approximation is good everywhere. But on the other hand, I've given up on the quality. I don't want it to be perfect or near epsilon good everywhere, yes?
Sorry to interrupt. So in the step 2 that you say, I get how you construct the GIs, but I wonder what is the final formula for phi? Because you say there exists phi, and it's kind of universal phi.
Yeah, so phi is phi, whatever it is the limit of these phis. Okay? So it's the limit of phi 0. So basically it's a step function that's in which you then subdivide, in which you subdivide each of the steps once again to get a finer step function, and then you subdivide again and make it even finer, and so on. So the limit of this is phi. And now if you're given a function f, it has and you want to approximate it, and you want to approximate it to within epsilon, well, it has a Lebesgue number, right? The Lebesgue number is the size of a square on which it would be almost constant, guaranteed. So if this size is 1 over 1,000, you look at the iteration level in which the steps are less than 1 over 1,000, okay? And you make the construction using that level. Okay? So if I wanted to approximate the Riemann zeta function badly, I would use the first iteration. And if I wanted to approximate it well, I would use the second iteration. And if I wanted to approximate it even better, I would use the third approximation, and no picture of that is available. Okay? Okay. So again, so now I claim that I can do, well, okay. Now I claim that I can approximate reasonably well in the L infinity norm. Okay? So at every point on the unit square, f minus the sum of the g's of g of phi I x plus lambda phi I y will be less, in fact, less than 2/3 or 3/4 of the norm of f. Okay? So I can do reasonably well everywhere. Well, but okay. Anyway, here's the proof. The proof is to use shifted chocolate bars. So basically, the different so basically you take the first phi that you constructed and you shift it 5 times. Okay? And here is what it does. Yes?
Why 5?
We'll get to it in a minute. Okay? So you shift it 5 times. So the brown image here would be the gaps in one of the steps for phi. Okay? If we shift phi a bit, the gaps, okay, the bad parts for the shifted phi are shown here in blue. And then the next shift, the bad parts are shown in purple, and then yellow, and then pink, I guess, whatever that is. Okay? And the point is that every point in the plane, oh, and I should have said, sorry, those shifts should be chosen so that they would work for all levels at the same time. But of course it can be done. Okay, so you choose the global shift so that the first level works, and then you shift again by a tiny amount so that the next level, so that this picture appears at the next level, and it hardly spoils the previous level because you've shifted by just a little in the second step. And then you keep going. Okay? Anyway, what's the point? The point is that now every point in the plane, most points of the planes are white. Okay? But the points that are bad are at most doubly bad. Okay? So here is a point like here would be bad for yellow. A point here will be bad for blue. But no point is bad for more than 2 colors. So every point is good relative to 3 of the chocolate bars, and bad relative to at most 2 of the chocolate bars. So there is a majority for good and a minority for evil. And now I've answered Rich's question, why 5? Because I want a majority for good, and there might be there may be 2 evil shifts for any given point. Okay? Anyway, now I actually also need to, I suppose each phi I will also be compressed so that the different phi i's have their values. So here is the G line, and the first phi I the first phi I plus lambda phi I, the first phi 1x plus lambda phi 2y will give values here. The second phi 2x plus lambda phi 2y will give values here, and so on. And so I can guarantee that I can color, that I can find the G that will color all phi's correctly. So here is an example. So again, this is the Riemann zeta function. I chose a phi with n equals 3. Okay? And here is the phi of x plus lambda phi y colored by G. And the colors for G were chosen on this interval so that when you look from above, it looks like a good approximation of the Riemann zeta function. Yes?
Sure, is 2/3 really 3/5?
No, it's 2/3. I didn't yet tell you what to do. Oh, wait, did I tell you what to do? Oh, I forgot. Yeah, G, in fact, is not the average. It's 1/3. So the appropriate coloring for G is to color it by 1/3 of the correct value. Okay, so that at each point you'll have at least 3 1/3 of good stuff. So you'll have the good stuff and 2/3 of potential errors. Okay, and now I've explained the 2/3. Okay. Anyway, sorry. So here are the colorings for the first 3 shifts. Here are the colorings for the last 3 shifts, and now I'll answer each.
So if you're in a point where, say, it's good for all the chocolate bars, then you're getting 5/3 of the value.
Yeah, so
But
I'm
that's
off
okay,
by
but it's still off by
2/3, but it's
2/3.
okay. Okay. The worst case, again, at every point here, I'll have at least 3 good ones, and at most 2 bad ones. Okay. If I have only 1 bad chocolate bar, I just take another one of the good ones and call it bad. Okay, but I still have a good majority. Okay, sorry. Anyway, and now if you look at these 5 shifted approximations from above, well, here's what you get. And in fact, it's a pretty good approximation of the Riemann zeta function. It's a surprisingly good approximation for the Riemann zeta function. Okay? And now, but here is the picture from in 3-dimensional perspective. And I guess the point here is that, okay, so I think this picture was made with a 2x2 approximation. Okay, and if you look at it with, given that there are 5 shifts, you'll find that there are 10 sort of flats in which the approximation is good. In between the flats in which the approximations are good, you have walls of bad stuff, or maybe trenches like here. And when 2 of these walls meet, like here and here, you'll have a spike of horrible stuff. But the point is that even the spikes are small in L infinity norm. So the highest spike in this region still doesn't reach as high as the total height of the function. And likewise, the deepest valleys the deepest trenches that appear here will not reach as low as the bottom of the function. Okay? Good. And again, this is the same from above. And again, you still have yellow stuff between good red stuff, but you never get blue inside red. And likewise, within the blue, you'll never see a red. Okay? We're practically done. The rest is an insult to you. Should I do it, being a bastard? Should I? Okay. Well, you know, it's basically standard iteration now. I mean, learn from the artillery, okay? So, you know, how do you aim, you know, you want to hit a sheep that you see in the horizon. You aim to it, you miss by 200 meters, you adjust and aim again, and now you miss by only 10 meters and so on. Okay, end of proof. So, in other words, define a linear operator, G goes to TG, so defined by TG is this sum that we want on the right-hand side of the Kolmogorov-Arnol'd theorem. I want to find a G so that F is equal to T of G. That's what I want, right? Now, T is linear. As an operator on the function G, it's just a sum of substitutions, so it's linear. So set F1 to be F, let M be the norm of F, and then iterate shooting and adjusting, like in the artillery. So you find G1 with norm less than M, and then set F2 to be F1 minus TG1, and then the norm of F2 is less than 3/4 the norm of M. 3/4 is 2/3 plus epsilon. Then you find the G2, so that G2 has norm less than 3/4 of M, and which shoots near F2. So F2 minus TG2, called F3, has norm less than 3/4 squared. And then you keep going to eternity, and when it's all over, you have a sequence of approximation to the differences, to your errors, and when you sum them all up, you get a function G, which does what you wanted, QED. Is it fair? Is it fine? I could not draw it. It's impossible to draw. Basically, at this stage, the spikes are already too sharp, and the difference between this and F is what we need to approximate now. So we will need to choose a tiny, tiny, tiny epsilon. Sorry, a tiny, 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 a large, large, large step size, a large, large, large bar size, chocolate, a very large number of chocolate cubes in our chocolate bar to get this approximation well, and it will simply not show on the screen. Okay, so that's why I stopped here. And since I still have a few minutes, I'll do propaganda. Yes.
So on step 4, why is the norm of G1 opposed to M?
Because G, where am I? Because G is you just copy the colors of F.
Oh, I see. So you never exceed.
There is no need to
You're
go
limited
outside.
Okay.
Okay? G is just meant to color the cascade with the right colors. You never need to go outside of the color gamut that you started from. In fact, the way I said it, I think you can even gain a third. Okay, because G has 1/3. I mean, you can divide each color by 1/3 because, well, that's how it works. Okay, sorry. Anyway, now the propaganda bit. So I have no good feelings towards PowerPoint, Impress, Beamer, any of these systems of presentations, and the reason is that they are completely against human nature. Basically, they force you, right? You are forced to stay within 30 seconds. You're forced to be at any time. Your mind has to be within 30 seconds of the mind of the speaker. You are supposed to be perfectly synchronized with somebody else, and no two minds are alike. So that's one reason. The other reason is that, I tend to think visually, or when I see a formula, I understand it. Then poof, it vanishes, and I have some vague recollection of what it is, but it's very hard to me to think of it after it vanished. Likewise, I cannot think of the future if I don't see it. Okay, so I don't know what I should be concentrating on right now, or if I tune out, I don't know when does the good stuff start, and I have to tune, and I can tune back in. So I think PowerPoint is just wrong. You know what I think is right, because I gave you copies. And let me just respond to one common objection, that it costs hours to make it, and it costs a few dollars to print those. So you're worthy of the hours, and the dollars. Well, each of you spent, I don't know, a few $100s to come here. Another 30 cents for a color handout is not a big deal. Okay? And here are the exercises. So generalize it to M. Rich, how would you, in the m-dimensional case, what would be the main difference?
It would be n-1 pluses.
What?
You have cubes instead of...
No, but sort of, what would be the main difference in the statement of the theorem?
Oh, you'd have more than,
So, okay.
you'd have more than 1 5.
Yeah. So instead of 5, it would be 2m plus 1 functions.
Right.
And in fact, also, instead of a single irrational number, you'll have to choose n minus 1 irrational directions to irrational coefficients for the different phi i's. Okay, and exercise 2, well, generalized to the non-compact case. It's actually significantly harder. It's not significantly harder. It would require a step 5. Okay, one more step. So it's 5/4 harder. Okay, and it would also change the statement of the theorem. Okay, I mean, the statement will be, so sort of the philosophical meaning would be, sorry about that. The philosophical meaning will be the same, that f can be written as a combination of functions, one variable functions and pluses, but the specific expression will have to change a little bit. And let me stop here.
Questions?
Yes.
This follows the original proof, the steps.
I have no clue. I mean, so the truth is, when I was an undergrad in Tel Aviv University, I gave a seminar on this subject. I read it in a certain book. I think it's the book by Lawrence on approximation theory, but I think I read the first few sort of pages of the proof and then just went on my own. And I never looked at it ever since. So everything ever since is sort of, I have no, I really don't know. I'm really not an expert on the subject. I mean, all I can do is make good pictures and say bad things.
I don't remember exactly, but first steps were done and published by Kolmogorov. Then Arnol'd somehow managed to finally solve it as a form as Hilbert proposed it. And once Arnol'd said me that matrix of a circle appeared inside this proof.
What?
Some dynamics of the circle appears in this proof, if I understood it correctly.
I don't know. I'm far from an expert. Again, as I said in the beginning, I've only given myself a candy within an otherwise miserable semester.
You just have the chocolate bar.
Yeah. Okay.
Yeah, can you do 4 functions, or is there some reason why you can't?
4 functions?
Yeah, instead of 5, I guess.
No, that's the question I answered. You need a majority for the good versus the evil.
Oh, no, I mean, I guess I mean, is there some heuristic reason why you can't produce 4 or 5 odds? I mean, it's some other method.
So the technique fails. If somebody else has a better technique,
Oh, sure.
then maybe, but I wouldn't know what to do.
I'm just curious.
Yes?
There were some respects in which your step 3 is worse than your step 2, right? So the question is whether you can have something that again has this, you can look at it at different resolutions and so forth, that both gets within epsilon on most and has a bound like this on all of the rest that doesn't have to bring in the artillery.
But the answer, you can increase the number of, you can increase 5.
Right.
Okay, but that will not converge, right? I mean,
and use the same technique.
in step 4,
Right.
right? In step 4, I need to know that with the same gun, I can approximate any f. Okay, so I cannot change the gun within the proof. Okay, now you're right that step 3 is in some sense worse than step 2, but again, they're both just, at the end you get sharp equality. So I mean, the theorem at the end is not about approximations. It's about the sharp equality. Yes.
I'm not sure if it's my order here.
Yeah.
But I wanted to make a comment for actually a set of 3 very brief related comments about your presentation, software, and the way you do this.
Yeah.
Number one, I think it's brilliant. Number two,
Thank you.
how do you do it, or do you distribute the software? And number three, however, you have to give anti-motion sickness pills to your audience. Because the way you move around there.
Oh, sorry about that. In fact, in some sense, the pill was built in, but apparently it wasn't sufficiently successful. So, first of all, the software is available. So, if you go to my website and go to talks and go to this talk, and when it will appear on your screen, it will say here, powered by handlebrowser.js, and that's the software. The second thing, the motion sickness business. So I've done my best to avoid motion sickness by, scrolling out. Sorry, by zooming out, moving, and then zooming in. And in fact, I've done it on the optimal path, so on the path that gives you the least blur, provably. And that path is the path in which at distance d, you can move at speed d, because things appear right when the camera is distance d from the screen, from the handout, you can move it at velocity d. And this is the right thing, right? Because when you're far away, you can move faster, proportionally. And do you recognize the metric?
Yeah.
So in fact, these were geodesic all motions in this talk were along geodesic hyperbolics.
But
Sorry,
maybe what you could
hyperbolic
do
geodesics.
as you zoom out, you could maybe dim the picture proportionally, and then you're moving on a dimmed picture, like with blinds, and then make it less dim as you come in. I must admit, I have a certain amount of motion sickness now.
Well, I've failed. What can I say? But this is open source, and you can. Sorry, Rich. Okay.
More questions? Okay, let's think.